In part 2 of the Unit 8 notes, we will be covering balancing equations. We know that we need to balance equations in order for our chemical equations to correctly show the law of conservation of mass. Step 1 of balancing an equation. You need to write out the skeleton equation for the reaction and make sure that all the subscripts are correct. If the equation is wrong, it's going to be impossible to balance it correctly. Now, for the examples that we're going to be starting off with here, I'm going to give you a correct skeleton equation, but eventually you're going to have to do this entire process from scratch. So you'll go from word equations, you'll write out the correct formulas, and then you will balance it after. For step 2, you need to record the number of atoms or ions for both the reactant and product sides separately under the skeleton equation. Polyatomic ions can be counted as one thing, but only if they're present on both sides of the arrow. So we'll see examples of that a little bit later. For step 3, you will add coefficients in front of each element or compound and adjust your count for each atom or ion under the skeleton equation until both sides are equal. Coefficients should also always be the lowest possible whole number ratio within your final answer. So for example, if your coefficients, you end up with something like 2, 2, 4, you would have to reduce that to 1, 1, 2. So it always has to be the lowest possible whole number ratio. So before we get to our checkpoints, we're going to be going through a bunch of examples that are already solved. So here we have a skeleton equation with carbon, oxygen, and we're making carbon monoxide. Now the first thing that you should do is write this out on paper, and then you're going to put a line through the arrow. You want to put each of your atoms on either side of that line, and I always make sure that my symbols are in the same order. So if I list carbon first on the left side, I'm going to list carbon first on the right side. That way you can quickly just look left and right to see if things are already balanced. And here we can clearly see that we have 2 oxygens on the left, but only one of them on the right. So we're going to have to fix that. All right, now what we're going to need to do is start to balance the equation. So if I have 2 oxygens on the left and only 1 on the right, I'm going to start by putting a 2 over here. Now when I do that, I fixed my oxygens, so now I'm going to have 2 of the oxygens, but I only have 1 carbon on the left, so I have to put the 2 over here as well. When I do that, that changes my carbons to 2. And then since the oxygen is now balanced, because 2 oxygens on the right, 2 on the left, I could just put a 1 in place here. Now, if you look up examples online, you probably won't see the 1 here. I still want you to fill in the 1 just so that I can be sure that you didn't skip that part. You're recognizing that it's already balanced. So you should always have a number in for a coefficient for each of your elements or compounds. In our next example here, we have H2CO3. It's breaking down into H2O and CO2. So I have my arrow, I'm counting up my atoms on either side, so there are 2 hydrogens, 1 carbon, and then 3 oxygens. On this side, I have 2 hydrogens, 1 carbon, and I have 3 oxygens because it's in 2 different places. So if it's in 2 different places like this, you need to add those atoms together for your total count. Now when I double check this now, I have 2, 2, 1, 1, 3, 3. So this is actually an example where just with coefficients of 1, this would already be balanced. And you might run into a couple of examples of this when you're going through your practice assignments. So if it does look like it's already balanced, it does not necessarily mean that you did anything wrong. You just fill in coefficients of 1. In our next example, we have PbNO32. We're reacting with NaCl. We are making NaNO3 and PbCl2. So I have my counts on the bottom. It looks like I have 2 nitrates on the left, but only 1 of them on the right. I have 1 chlorine on the left and 2 of them on the right. So those are 2 atoms that are going to have to, or 2 ions that are going to have to be fixed. So I could start by putting this 2 in front of the sodium nitrate. Now when I do that, that changes the nitrates to 2, so that fixes that part. But it also throws off my sodiums, because now I have 2 sodiums on the right, but I only had 1 on the left. So then I would have to fix that. So that was fixed here by putting a 2 in front of the NaCl. That changes sodiums to 2, changes the chlorines to 2 as well. And now if I double check my count, 1, 2, 2, 2, 1, 2, 2, 2. So now it is all fixed. Any spaces that were left empty before, I put coefficients of 1, and now I have a balanced equation. Notice that in this example, I counted the nitrate as a single thing, NO3. That was because the nitrate was present on both sides of the arrow. If I had nitrate on one side of the arrow, but then it broke down into the individual elements on the other side, I would have to count the individual elements instead. In example 4, we're going to see an instance of that. So here I have a hydroxide on the left side, but there's no hydroxide on the right side. So if I tried to count the hydroxides, it would be impossible to balance. Same thing is true over here. I have a carbonate on one side, but no carbonate on this side. So I'm counting my 4 individual elements. So to start off with, I have 1 sodium, I have 3 oxygens, because 1 here and 2 there, and I have 1 hydrogen and 1 carbon. On the right side of the arrow, I have 2 sodiums, because there's a subscript of 2 here. I have a total of 4 oxygens, because there's 1 there and 3 there. I have 1 carbon, and then 2 hydrogens. All right, so looking from left to right here, it looks like the sodiums are not balanced, the oxygens aren't balanced, the hydrogen isn't balanced. Carbon's the only one that is currently good. So I'm going to pick one of those elements to try and balance first. So why don't we try to balance the sodiums? I could fix the sodium by putting a 2 out in front of this sodium hydroxide. When I do that, it changes my sodium to 2. My oxygen, I now have 2 over here because that distributes across, but I also had the 2 from over there. So now my total goes from 3 to 4. It's a very common mistake for students to just take 2 and then they look at the number down here and they change it to 6 because they're doing 2 times 3. The oxygen is in 2 different places here, so that would not work. So 2 times 1 is 2, plus the 2 from over there is 4. My carbon doesn't change because it's over there. And then my hydrogen, 2 times the 1 was 2. So by doing this one action, I actually balanced everything. So I'm going to put 1 as coefficients in each of the other places. All right, so now we're going to be going through a checkpoint, and this one we're going to be solving together from scratch. So I'm going to place my line going through the arrow. I have 4 phosphorus, and I have 2 hydrogens. On this side, my phosphorus is 1, my hydrogen is 3. So I need to pick an element to start balancing here. I'm going to start with my phosphorus. So I had 4 on the left and only 1 on the right. So I'm going to put a 4 here. When I do that, 4 times 1 is going to be 4. But that also has an impact on my hydrogen. So 4 times 3 is going to be 12. Now on this side, the hydrogen is by itself, so I can put a number here that will only affect my hydrogen and it won't change my phosphorus number, which is good because phosphorus is currently balanced and I don't want to change that. If I put a 6 here, 6 times 2 would be 12, and now my numbers on the bottom match. I could put a 1 right here, and my balancing here is 1, 6, and then 4. For our next checkpoint, here we have SO2, H2, H2S, and H2O. So I'm going to put my symbols underneath. I have an S, an O, and an H. S, O, H. Sulfur, I have 1. Oxygen, I have 2. Hydrogen, I have 2. Sulfur, I have 1. Oxygen, I have 1. And hydrogen, I have 4 because it's in 2 different places. So I have 1 there and there. So I need to pick an element to balance. There are 2 that are currently unbalanced, the oxygen and the hydrogen. Since hydrogen is by itself here and will be easier to balance, I'm going to start with the oxygen instead. So in order to make the oxygen on this side a 2, I'm going to have to put a 2 here. That will change my oxygen to 2, but notice that it also changes my hydrogens. Now, again, you might think that it would be 8 because 2 times 4, but the hydrogens are in 2 different places. So 2 times 2 is going to be 4, and then I'm adding to the 2 that was over there. This is actually 6 hydrogens. All right, next we have to make the hydrogen on this side 6, which can be done by putting a 3 here. 3 times 2 is going to be 6. 1, 2, 6, 1, 2, 6. Everything is now balanced, so I can just put 1s in any places that did not require a different coefficient. All right, for our next checkpoint. This one is going to be a little bit trickier. So I have a carbon, a hydrogen, and an oxygen. Carbon is 2, hydrogen is 2, oxygen is 2. On this side, carbon is 1, hydrogen is 2, oxygen is 3, because it's in 2 different places. I have 2 over here and 1 over there. So I'm going to start by trying to balance the carbons. I'm going to put a 2 on this side, because that would change my carbons to 2, but it also changes my oxygens. I have 2 times 2, which is 4, plus the 1 from over there. So I now have 5 oxygens on the right side. My hydrogens look like they're already balanced, so all that's left is to make this oxygen a 5, and this is why this one's a little tricky. There is no whole number that I can use to make this oxygen a 5. Now there's a little trick to this. You do have to have all whole numbers in your final answer, but you can use a 0.5 as kind of a stepping stone. So if I wanted this to multiply out to 5, I could put a 2.5 here. 2.5 times 2 would give me the 5 that I need, and now all of my numbers would match up. So that's a ratio of 1 to 2.5 to 2 to 1. Now in order to make these all whole numbers, all I have to do is multiply each of these times 2. That would give me a coefficient of 2, a 5, a 4, and a 2. So those would be the actual final coefficients that I would use. Now there are other ways you can go about doing this, but I found that putting a 0.5 in as a placeholder is the easiest way to try to solve these trickier balancing problems. All right, so that is the conclusion of part 2 of our Unit 8 notes. In our next part, we are going to be going through classifying chemical reactions.